In this video, we're going to talk about something interesting called confinement. We know that quarks come in groups of 2 or 3. The groups of 2 have one antimatter quark, so here I've got anti-charm, and they have one regular matter quark, so here I've got regular old top. Confinement says that you can't ever get one quark by itself, and there's a specific reason why this is true. Here's what happens when you try to separate these two quarks from the meson. You pull them apart and a force is exerted. You pull them a little farther and the strong force actually grows. You pull them a little farther and the strong force grows again. And you pull them a little farther and another pair pops into existence. Notice it's a antimatter pair. We have down and anti-down. And what has happened? You started with one meson, and by trying to pull it apart, we wound up with 2 mesons, more matter than we began with. How is this happening? To answer that question, we have to use mass-energy equivalence. The big idea here is that when you separate the quarks, you add energy to the nuclear field, the strong field. Okay, so how do we visualize that? Well, instead of the strong nuclear force, pretend that it's a spring connecting the quarks. So here they are, they start together, and you pull them apart. But by pulling them apart, you stretch the spring, so there's now energy stored in this strong nuclear field. And you pull them farther apart, and now it requires even more force. You have to put in even more energy into that strong nuclear field. And then you have to pull even harder, so you put even more energy into the strong field. And before you actually separate them completely, you reach the threshold for pair production. In other words, right at this moment, you've added so much energy trying to pull these apart. You've added so much energy that you've now reached the amount required to create a matter-antimatter pair. The top 2 pictures show this with mesons, which have one quark and one antiquark, but the same thing happens when you try to split up baryons, which have 3 quarks. When you start pulling one apart, you add so much energy into that strong nuclear field, or sometimes we call it into the gluon field. You add so much energy into the field that you've now got enough energy to spontaneously create pairs of matter and antimatter. Now, in reality, we're not taking our fingers and pulling the 2 quarks apart. We're not using tongs, right? Quarks are way too small to grip with your hand. So we're not pulling these. How do we add the energy then without pulling them? How do we split them apart? The answer is particle colliders. The biggest of these is the Large Hadron Collider. It's underground and it lies below France and Switzerland, and it's the single largest machine humans have ever built. So let's look at how it works. 27 kilometers. So here's the proton going through a first initial booster. There's another acceleration process, and there's one final acceleration process before we enter the main ring. The SPS, they have cool names. This one, for example, is the Super Proton Synchrotron. And you can see that this little ring is not so little, it's 7 kilometers. And then they enter the 27-kilometer main ring. They move around several times. We can take a look inside. There are these tunnels, and the motion of the protons is controlled using magnetic fields. So the protons are speeding along. They've been accelerated to almost the speed of light. There it is with a massive amount of energy. You can see the 3 quarks inside. And here they enter one of the crossing points. They slam together. We've got 7 detectors placed to collect various measurements. And watch what happens. The jet stream, the particle stream of all of these matter-antimatter particles. And we can observe these using the detection mechanisms set up. The final thing for us to learn is the range that these forces have and their relative strength. You could probably guess which one is strongest, the strong force, but which one is weakest, do you think? Well, before we get there, let's talk about range. There are two forces which act at an infinite range. The gravitational force and the electromagnetic force, they both depend on 1 over r squared. So in theory, r can be infinity, and you still have a gravitational force. It's just so incredibly small you would never be able to measure it. What about the others? We know that these are the forces inside of a nucleus. So the strong nuclear force acts at the diameter of a nucleus, 10 to the minus 15 meters. That's the range over which it acts. The weak nuclear force acts over even smaller ranges. The relative strength of gravity we will call 1. So we're going to measure how strong are the rest compared to gravity. The next strongest is the weak nuclear force, and look, it's not so weak, is it? It is 10 to the 24 times stronger than gravity. Next up, the electromagnetic force. It's another 10 to the 11 times stronger than the weak force, but it's 10 to the 35 times stronger than gravity. Finally, the strong nuclear force is only 100 times stronger than the electromagnetic force, making it 10 to the 37 times stronger than gravity. You all know what the exchange particles are, except for gravity, because we have not yet discovered a model which accounts for gravitational exchange particles. But you can go ahead and fill in the rest of these. The weak nuclear force has 3, recall. And what are the particles that they act on? You can fill in these 3 boxes using quarks, charged leptons, and uncharged leptons.